dump and you still really don't know. Oh, yes, I guess there's the title there. You can, if you want, just go and export. And I'm pretty sure Sam is cool. If you guys have been exporting his notebooks, they're all in here as well. So they're under Jupyter, TensorFlow, fundamentals. All right, here's Fabrizio. Yeah, what are you talking about? The distributed? Yeah,
yes.
Okay.
Okay.
Mic?
I think so. Everything is okay?
Is it green?
Unplugged?
Green, okay.
Cool. Hello, everyone. One is awake. Let's see. Hello, everyone.
Hi.
Hey. Good. So let's see. Let's make things more confusing. You know how it works on one session on one node, but the real power of TensorFlow. Can I remove this? Yes. Okay. So the real power. Did any one of you ask why a graph? Why a node? Can't we just use like all the other programming language where we have our language, we define the code with Java and Python and just it works? So with distributed TensorFlow, it makes realize how important is having a graph. So this is an animation that is in the TensorFlow website. I don't know if you guys are able to see it. Seems okay. So as you see, the data is being propagated over the entire graph of your computation. And once we have this operation separate, we are able to assign them to different nodes and to different, the specific term is devices, okay? So let's go in detail of what that means. So we start with the concept of cluster. In TensorFlow, a cluster is a set of workers. It's a set of jobs, and each job has a set of tasks. Usually, you can define any kind of jobs, but usually it's two sets of jobs are defined. One is called worker, and the other is parameter server. The worker will execute operations, and the parameter server will be storage for all the variables of your graph. Okay, so think. Going back here, you can think you see the square are your variables and the round are the operation. So this operation will be run on workers, and these variables will be will live in a parameter server. And TensorFlow allows to communicate all this information across your nodes without you having to manually code all the transfer of information between your nodes. This is an example of a cluster specification where it's just a Python. It's a Python dictionary where you specify the nodes, and in this example, I have a parameter server. I have two parameter servers and two workers. And this is just a trick to evaluate this string as a Python dictionary. And out of this Python dictionary, I'm creating what's called a cluster specification. Okay, and from this cluster specification, I can see what are the available jobs for this cluster, and for each job, I can see what tasks are assigned to that job. Make sense? It's a way of, let's say you have 1,000 nodes and you want to define part of your nodes have to do a specific job, another have to do another specific job. And why we do this is because the transfer of information between these nodes is intensive. So you want to be able to effectively use the resource of your computer to communicate across your entire cluster. This is how TensorFlow define a device. Okay, so there is some syntax here. So it's a job, and the role is a worker, and then its task number is task number 0. Okay, this is just a way of identify the role of each process. And the same thing with parameter server, but in this case the job is of being a parameter server. We keep going with the pinning of variables. Each variable is assigned to a specific device. What does it mean? You guys are now TensorFlow experts, so you know what a variable is, I hope. Okay, so each variable has a device assigned to it. Device is specified with one of these strings. Okay.
Which notebook are you actually browsing?
This is not public, not a book, so you have to follow on the screen. I will put it public. It's not public because if everyone starts running this, then the only cluster that we have running, it will crash. Okay, so each variable has a specific device. At this moment, no device has been specified for this variable. Okay, because it's just a generic. Variable. Has not been pinned to a specific device. When I say device, think at the low level, it will be assigned to a CPU, a GPU, or any other compatible TensorFlow device. Okay, so this is a way of assigning where that variable will live. But we can enforce the device of the variable, and to do so, we use TensorFlow.device, and in this case, we are pinning the variable myvar to one of the parameter server. Okay. So just imagine the memory of your nodes that are parameter server. Every time someone wants to use this variable in the graph, it has to go to that parameter server to fetch the contents. Okay, and the device will not be changed now. So this variable will always live in that specific device. And of course, we will have to specify for each variable what is the exact device that will live on. Okay. So how does this work? We have the node, we have the memory, we assign a variable. Let's begin again. We have a node. We launch our Python process. The Python process imports TensorFlow. TensorFlow constructs the graph in memory, sees what are the variables of the graph, and then it sees which variable he has to request to the parameter server. But how do I do a request to a parameter server? You have to launch this process inside each node of your cluster. Okay, so you have all your machines ready and running, all connected with the Ethernet between them. You launch the Python process, and inside this Python process, you launch a TensorFlow server. The TensorFlow server is very simple. It's just these lines that you can see here. You launch a train.server, you pass the cluster definition, and this is the cluster definition that we saw earlier. So you have to specify who can talk, which are the nodes of your entire cluster, because they can send the variables to each other. And then I specify what is the job of this node, okay? And then what's the task index. And so you can see if I have a node in this cluster, how many nodes do we have? We have 4 nodes, and how many jobs? We have 2 jobs. We have 4 nodes. Okay, each one of these will be a TensorFlow server. Okay, the TensorFlow server will read this string, and it will say, okay, who am I? And so the first one say, oh, I am the parameter server, and my task is task 0, okay? Because they assign the task based on where are in this list. So node goes up, node 0 goes up and takes this one. Node 0 is going to be job parameter server task ID 0. Node 1 will be job PS task 1, node 2 will be worker 0, and node 3 will be worker 1.
Are there any resource requirements of parameter server versus worker? Which one needs more memory and more?
Yes, that's, for example, this is a good question. Question is, do the job and the task matters based on the machine that you have? It does. Okay, a parameter server, you want to put a node that has a lot of memory. Okay, while a worker, if you have nodes with GPU, you want the GPU nodes to have worker. Okay, it doesn't make sense to have a parameter server with GPUs because they will be not used. Okay, so now you can see each one runs this and extract the definition, and it just waits for a request. Okay, so it opens a port, the port that we specify, 888. It was going back. Where is it? Here. See the port, and we'll listen for request. Okay, so at this point we have a client and a server. How do we communicate to the server? This is our configuration at the moment, okay? The way that we communicate is through GRPC, that is a remote procedure call based on protocol buffer. Don't know if you guys are familiar with GRPC and protocol buffer. So the idea here is we need to transfer a lot of information on the wire. Okay, if we do it with HTTP on text, it's going to occupy a lot of bandwidth. GRPC defines a protocol to serialize this data in a very efficient format. Okay, so it's binary, it's compressed, and that will lower the time to transfer from one node to the other. Okay. And the remote procedure call is a set of specification that allows to execute function calls across nodes. Okay, you know that you can run within your own process, you can launch a function. Okay, but how do you launch a function on a different machine? That machine could also not have the same language. Okay, we want to create an interface of saying, launch this function that has this signature on this other machine. And so GRPC allows to do such specification. You say, okay, I want a function that takes an integer and returns an integer. Okay, and at the low level, how actually this works. So we have our client, we have our variable, okay? First, the client takes this variable. At this point, the variable is in memory, okay? It's just numbers in memory that as a tensor inside our Python process. The Python process says, okay, I have to transfer this, I have to do a remote procedure call And this call, let's say add1, takes this variable. So the variable gets serialized using the GRPC protocol. It will become like a binary string, and this binary string will be sent over the wire to the server. Okay? Okay, so we have this variable, we have serialized it. It's a bunch of just numbers, completely different from the representation that we have in memory. Will be sent over HTTP. And here, one novelty of HTTP2 is of gRPCs that use HTTP2, so the connection stays alive, and that's good because it improves performance of the whole system. And then when it gets so this bunch of binary gets to the other server, and at this point the server receives this binary. It will decompress, deserialize this variable, and it will assign it to memory to the local Python process of the server. Okay, and now you can think having this in place, we can share variables across our node. Okay, because each node has the cluster definition. That means they know each other node. Okay, so I can send from here to here to here to here, or from here all the way. Okay, as soon as I know the IP and port of the other gRPC server, I can communicate with it and share information. But I also can invoke a function. Okay, so I can tell to one of the nodes to execute part of the graph. Okay, and this is important. So given a graph, I can take nodes and the variable. I know which variables an operation requires. Okay, that's defined by the graph, and I can say to another server, okay, execute this node. The server will see, okay, this node requires this variable, and I know the variable on which device are, okay, because we specified the device. And so each node can go and say, okay, parameter server, give me this variable, give me this variable. I will execute the operation and return a new variable, and the new variable will have a device specified. If I am the server of that device, it will stay in my memory. Otherwise, I will send it over to the other node. Okay? How confusing is it? Okay.
Is there a question?
Oh, yes.
So, this is for training only, or can you use this for serving as well?
This is usually used for training.
The docs say only for training.
Well,
So you can't use it like a distributed system to serve these models?
it will not make sense, because you don't need, once you create the model, then that is only one step. Like you just make it a forward pass and you get the result. So you can scale it by just duplicating the model. So if you want to handle a lot of requests, you just copy the model over 1,000 and put a load balancer in front of it, and it will manage that part. Okay. Yes?
Earlier when we were talking about the session object, there was like a target, and you could specify a remote target. How does that differ from the sort of like distributed workload model here and sort of the object model you're using for defining like the parameter servers and the worker servers?
Okay, so the question it was, you guys have seen the session, and the session has a target. So the session is the client, okay? So, and the target is the server. What happens when you have only one node is that TensorFlow implicitly will create a server inside the same process. Okay? And of course, all the communication, it will be in process. It will not be serialized. Okay? Because I have already everything in my own memory. Okay, so the session you have to see is a client, and the server has a very specific interface, and base, if it's a remote server or it's a local server or it's an in-memory server, it will do the connection, the fastest connection available. Yes.
So if multiple workers are updating the same variable, do you care about serializing the data operations?
If the same?
If multiple workers are working on the same variable at the same time, and they update, they write or do whatever updates, do you care about serializing the updates so that the master gets the actual, serialized?
Yeah. So that's actually we're gonna talk about that later. Okay. This is an example of a protocol buffer. This is the actual protocol buffer of a variable from the TensorFlow code. And it's simple. What's the variable name? What's the name of its initializer? And what's the name of the snapshot? Okay. So there is no content inside the variable. It's just a tag of where the actual memory is. Okay. And anything that can be serialized, it has a 2-proto signature. So you can see exactly what will be serialized across the wire. And so yes, like you have variable 24, and that depends on how the graph is being built. Okay, so let's get a bit concrete. What we're going to do now is a simple reduce sum, okay? The map reduce in TensorFlow. In this example, we will going to have an array of ones, of 1, 1, 1, 1, 1,000 times, and then we're going to ask the worker to divide it, and each worker will sum 500 of those. And then the final result will be summed at the end. Okay? What will be the final result of a reduced sum 1,000? 1,000. Okay, 1,000 times. Okay. Let's go step by step here. But you should already know all of this, right? Here we define a graph. At this point, it's just an empty graph, okay? All the variables. There are no variables. Then we say, set this graph as default. I mean, all the variables that will be declared inside this context, no? Inside this context, it will be assigned to that graph. And only this graph, okay? Here, we are pinning our variables. So we say, I want an input array, and this is just a placeholder of an array that has one, this is just an array, okay? This is a way of saying that the array has an unspecified length. Okay, you can pass any length that you want as an array. But it is an array, so it has rank 1. And then we want the final result. That is just, at the beginning it's 0 because it's a good, if we pass an empty array, the sum is 0, right? Then what we do, then we initialize all the result. So we do a split on the first, rank. So in this case, if you think 1,000, we split along the first dimension. And then we split based on the number of workers that we have. Okay, so this is just a very naive way of splitting the work. And input array is what we pass in as an input. And then I do some Python magic. I don't know how many of you are familiar with Python, but this, it will zip, so it will return one element and one element from the two array, and then enumerate, it will just put the index of the sequence. So it will be, this will be 0, the portion will be the first part of the array, and worker will be the worker assigned to the array, and so on. And then we pin again, but this time we pin the operation, okay? So here we are pinning the variables, and we are pinning it to the process parameter server. Okay, so this is our big memories node that have 64 gigabytes. And then here in the workers, we have our GPU nodes. Okay, and here we are saying pin these operations to this device. So what are the operations? We do a reduced sum of the portion. Okay, so we just sum within that array. Then we use this utility function that's very useful if you're using TensorFlow. It's tfprint. Okay, so it will just print the message. We're gonna talk later of how to use that. And then we want to save all the reduced results in our list. Okay, so we have the list. Should I right? So we have our big list, and we split in two. Each node will take one of the two lists, 500 and 500. We reduce those 500. We do a sum over those 500. We get one single number. Okay, so the other node does the same. So we have two single numbers. Then we have to sum these two final numbers into one. And this is what we do. With final result, reduce sum. TFPAC is to get a list of tensor, a Python list of tensor, and that converts to a tensor. Okay, because TensorFlow doesn't deal at all with Python object. Everything gets transformed to a tensor. And each operation, you pass a list of tensor and you get a list of tensors. So, and all the tensors are immutable. So you cannot change a single tensor. Okay, you have to create a new one completely. And this can be confusing if you are trying to just change one single element of your array. Okay, TensorFlow will require you to create a complete new array. It's one of the most asked questions on Stack Overflow. So we'll save you the pain. Okay, and then we just reduce the final two objects, and of course we will have our final result. Okay. So what we have here. So here are our 4 nodes, okay, that we showed it before. Okay, Chris set up those for me. These are the 2 parameter server. These are the 2 workers. Okay, very simple. And I SSH into them and just start the server job that we saw it before. Okay, they say, okay, start tf.train server, and each one I said, okay, you have to be parameter server 0, parameter server 1. You have to be a worker 0 and a worker 1. Okay. And now these are just listening on those ports. Then I'm going to connect with my session, and I can target any of the nodes, because each node communicates with all of the other ones. Okay, so here I'm connecting to one of the nodes, and I'm passing the graph that we built earlier. Here I pass some session configuration just for habit. This tells you on which device goes which variable. And then I'm running final result. Final result was the final sum of the graph, and then we have our fit dictionary. We pass our input array. This is a NumPy array of 1,000 with all ones inside. Okay, if you guys don't believe it, there. Okay. I don't know if you guys know this trick. If you do Shift Tab inside the IPython session, it will show you the documentation for that function, and this saves for any function that you imported with Python. Okay, and so it's Shift Tab, and you can read and without getting out of the context. Okay, so we run the final result. This one will communicate with all the servers, and this is everything is empty here. Just hey, let me see. Okay, so it's gonna print something when it actually communicates. Hopefully, there, 1,000. So it's working. And here we see that you guys remember that the TF print operation that we insert in the graph. So here is that operation printing on the standard out of the server. Okay, if you guys maybe not able to see that. Okay, and let's go back 1 second for what we was printing. So what we were printing is this was say each time you execute this local reduce node, print this value. Okay, and you can add the message. So portion is, and then you pass what the portion is. And this way is 500, 500. Okay, you can see here a bunch of messages of communication between the nodes. Okay, another thing that you can do, you can inspect any variables inside your cluster. Okay, if you want to know a specific variable in some node, you just pass it to the session.run. So for example, this is local reduce, and local reduce is how can we know in which node is local reduce defined? Dot device. Okay, so this one is in the worker 1, and at this point I just execute and the worker 1 will show it again. Okay. So this is a very basic example of trying to understand how everything works. Time for questions.
Isn't local reduce on both worker nodes? Like they both have their own copy?
Yes.
So why did that print only one device?
Because here we have a 4, okay? So what happens is for each worker, in this case 2, pin every operation that they define after to this worker. So here we are creating we are creating 2 similar set of operations. Okay, so we have the local reduce mapped to 0, and then the second one will be mapped to 1. And being the last one being defined, then is the one that you actually see out of the context. Otherwise, that's why I have to keep a list if I want to reference all of them outside the context. Okay?
Also, this final result calculation is happening in the parameter server, right? This one, yeah.
This one?
Yeah.
Let's see where is final result. It's an operation. Let's see. No, it's not being assigned. So this one, probably the local session will handle it. Okay, so any more questions with this example? Because then we go distributed with the neural networks. That's a bit more advanced, but it's where actually you want to be. So everything here is clear. It's clear how the nodes communicate, GRPC, the role of GRPC inside it, how do you pin a variable to a node, okay, how the session connects to one of the nodes of the cluster and sends what operation wants to execute, okay. Once you define your graph, this is important to have it clear. So once you define your graph, you can ask for any operation of the graph. And TensorFlow will figure out what's the sequence of dependency of that node and execute them. Okay? All that is done under the hood. So you can ask, okay, give me this variable, and then give me this little this other operation, and give me out what's the result of it. It doesn't have to be always the same operation. You will see in the example to be always the optimized step, because that's the most common to do, but you are not limited to that one. Okay, you guys ready for the distributed convolutional neural network? All right, you asked for it. Hold on. Hold on, I lost it. Okay, here it is. Can you guys see it? Okay, so at the beginning we have the same, this, yes? So the question is, how does TensorFlow partition the variables across the cluster? Yes, so one way is doing manually, as we have done it with the tf.device. Okay, so you manually say this variable here, this variable here, this variable here. And the other way is using an auto-assigner. Okay. So just to go, this code is the same code of the convolutional neural network. Downloads, prepares everything. Until we get to the cluster specification. This is the same cluster specification and the same cluster we have been using until now. Okay, so you don't have to do and change anything on your cluster, even if you change the model. Okay, this is important for a company where you can have your cluster all set up, and each data engineer can run its model on the same cluster. You only need the cluster specification to run it. Okay. So what we are doing here is so this is the same model that we have before, just changing the construction. Okay, we have our weight variable, our bias variable, how to create a convolution, 2D convolution. Yes.
So if you have one step in your graph that's more computationally expensive than the rest of the steps in the graph, is there a way to distribute that node across multiple nodes in your cluster so that you can run those in parallel and then kind of skip the bottleneck, so to speak? Because it sounds like right now you have a graph and you can distribute the task of that node, of a node in the graph, to a given worker. But can you distribute it across multiple workers at once for that same node in your TensorFlow graph?
If you want to run the same operation on multiple nodes, you can. And so as a strategy, you can either have the same entire graph on multiple machines, or you can have one graph with multiple subgraphs on different machines. Okay, and in preparation of this question, I made this. Don't crash it, no. I think it's well, but you can kind of see it, no? So we have the two graphs that are completely identical. I'm going to try to. You have the two graphs that are completely identical, this one and this one. And then you have one graph that has multiple subgraphs. Okay, and so you can say, okay, this subgraph send them over to different machine, and then I will accumulate the final result. And this is what we're going to do with the distributed convolutional neural network. So this is the same procedure as our simple reduce sum operation, but of course we have many more operations inside to create the convolutional neural network. So rough model in your mind is you have this set of 4 layers, and each layer communicates with the next one in one way, and then back when you want to optimize the weight based on the results. What we are doing here is we are using this device setter. I'm not sure if you are able to see it, but TensorFlow.train.replica device setter. What this does, you don't have to set it manually. Okay? Remember how it's pretty tedious to say, okay, this variable on this node, this variable on this node. What if you have 10 or 20 parameter server for a big job? What this does is it takes all the parameter server and automatically assign it in a round robin way to different parameter servers. So variable 1 will go to server 1, variable 2 will go to parameter server 2, and so on. Okay? And then we have the same structure. We say, okay, with this device setter, okay, this is not anymore a device string. This is our object device setter. So you can create some logic inside that on how to handle. And then we have our placeholder, that's the input data, and all the same L1 bias and weights. this is the same thing as you guys already saw in the previous example. Okay, the only thing that's changed is that we are setting we are pinning that variable to a server. Okay, and I'm doing it in an explicit way. I could have created the entire thing without. I could have created a function that does this, and so I can run the function on my local machine, and then when I'm ready to distribute, I just call this function from within a TF device context. Okay, this is a bit. Hope you guys follow me. It's a bit advanced. Took me a bit to grasp it. And so these are all our variables. Okay, this first step, we assign all our variables to our parameter server, and now we are ready to distribute the workers, the job on the worker. And so we have the same splitting logic to say, okay, for each worker, create this graph. Okay, so we have all the parameters, all the variables ready, and then we start creating the same graph on each node. And now we have 2 workers, so we create two graphs. And we will create model, the entire model based on a portion of the input. Okay, so we're going to have a batch of information coming through. Okay, and we will split the batch. And we'll say, you do this first part of the batch, and you do this other second part of the batch. And then we will do the same thing. We will sum the result. And the difference is, at this point, we'll go back and back-propagate the values through the weights. Okay? So we define the device, and then we define the optimizer. We say, okay, reduce the mean, use an optimizer, and I want the mean loss to be as low as possible. And the loss is just the sum of all the losses, okay? And we create some scalar summaries and other details. This is, when you start working a lot with TensorFlow, it's good to know the supervisor. This supervisor will take care of some parts of the work, like saving your model. This training can go on for a week. You don't want the cat coming on the keyboard and stop the process, and you lose half a week of work, right? This supervisor will save it to disk each number of steps. And if it crashes, you can relaunch the system, and it will reload from those checkpoints without having to lose all the information. So if you can think, your variables will be serialized and put on disk. Okay, and when you restart, it will be deserialized from disk and put back to memory.
So is that partly doable because tensors are immutable?
Yes, because you have this snapshot of the tensor. No, like remember that when the variable has different fields in the protocol buffer, and one of that was snapshot. So you can say, okay, you can have different snapshot of the same variable, but the content varies for each snapshot, right? Okay. So the supervisor, it creates a bunch of information, of services for the training process. And this is how it's done by Google. This is state of the art for TensorFlow. Instead of creating a session, we use the session that's been created by our supervisor. Okay, SV is supervisor. and prepare or wait for session is the same parameters that we have for the session. Okay, so just read here as train tf.session. We have a summary writer, and at this point we start cutting our batch, and we say, okay, this is our batch data, and this is the labels that you have to train, and just run the optimizer on this batch data. Okay, each 50 step will print the loss, and at the end we will get the final result. So now I'm going to execute this job. So it's preloading everything, doing all the image information, all the image compression and resizing that you do at the beginning. And we can see here that the two workers are training. Okay, one of the steps of that graph was to print the loss and the global step. So this slows things a bit because you have to flush the standard out, but it gives you some feedback. Otherwise, all this time it will be just empty and you don't know if it's working or not. And so we are processing our mini batch. Before it was 32. With this one, we are processing 256 images at once, but we divided each worker will have half of that. Okay, and the number of steps is the same. Hope it didn't crash. No. So, of course, and you realize, like, just specifying almost the same graph, you now can distribute the computation over 2 nodes in this case, but no one will prevent you to distribute to 1,000 or more. Okay, at certain points of distribution, other scalability should come in play. But if you have 1,000 nodes, it's already a good problem a good step to be in. So. Another good thing to know. Fabrizio, what if you don't have a cluster? No, like I just have my own machine. How I can test this one? You can run local servers. Okay, remember the train.server at the beginning? You just specify it as a localhost. Localhost and port 888, and then you launch another local process and you say localhost port 889. Okay, in this case you have 2 servers. Then you start your session. You connect to one of the 2, and you keep running your graph. And usually you hit all the code base already. At least you know that everything should work. Another trick that I want to mention is the size of your of the serialized data over a protocol buffer. It has a hard limit. So if you are sending big, like 4 gigabytes or more of data, it can crash. And there are online, so if you see it crashing, it can be that, and there is a patch that you can apply to have more bigger array. But usually it's a sign that something is not working in your code.
Like 4 gigs between 2 nodes or overall?
Between 2 nodes. In a single tensor. You can have 10 of 4 gigabytes and should be fine, but you cannot have 40 gigabytes in one tensor. Okay, and the reason is because the variable that specifies the size is int 32. So. So the machine keep cranking. I think I set to 2000. It should be almost there. In the meantime, we can. I launch a TensorFlow, a tensor board on that machine. So let's take a look. I think this is because. And this is something very cool that you have to notice that you have to know it to notice. That's it. I think the recording is killing my machine. What is it? TensorFlow. Here. So I launched a simple tensor board from the directory where I was running. And as you see, we can see the graph. Okay? But what do you guys notice on this graph? One thing is you can specify the color by structure, okay, or by device. And this is very useful because in this way, you know exactly where each variable is. Okay? It's a little switch here. And here, for each color, there is the device specification of where it's being assigned. And so you can see this is an operation, and you can see the layer 3 weights is on task 1, and the bias for L3 is on task 0. Okay, and this for each of the operations. Then you can see the answer to the question that we did earlier of we have two graphs. Okay, so this is well, we have one graph, but we have the convolutional layers replicate on two nodes. Okay, this is in one worker, and this is in another worker. And of course, both of them have the same variable from the same server. Okay, and then you can think how this can become bigger and bigger, and you can visualize more. Well. We get the same accuracy of the normal model, but we have been trained on more examples. Usually that tells that we need a better model itself. It's not a matter of training. More data will not help at all. Okay, we need something in our model that is able to shape a better distribution. Okay, I think this is the main gist of how to distribute graph of TensorFlow over your cluster. I would like to, one last thing that I want to say about TensorFlow is don't think TensorFlow just for machine learning or for deep learning. Okay, this is a generic computational graph. And you can execute basically anything that is mathematical, that can be defined as a set of operations. And what I wanted to show is, well, it would be better to start here. I'm gonna kill this thing. So you can do arbitrary set of operation until to just create a Mandelbrot image. And here there is nothing this is just a set of mathematical operation. There is nothing machine learning TensorFlow or deep learning. There is TensorFlow, but there is not deep learning. Okay, and that's it. If you guys want more, let me know. But I guess it's a lot to digest. It took me a while to actually get grasp of all the definition, worker, job, task. I hope I help you in that direction. Yes, we have a question. Yeah, there is a small company in Mountain View, Google, and apart from Google, I think I'm not aware of like directly. Yes, it's pretty recent. I guess only very eager startups are just putting it out and see either it crash or not. Google has been using it internally. The testing is pretty thorough. There is a TensorFlow serving that is not the TensorFlow server that we saw. Then TensorFlow serving, it will create an RPC server, but it will only execute a subset of operations. So you just launch that and you train your model, you save it. Okay, so you have a checkpoint of all your weights on the graph. Then there is a process that you can remove the variables and make them constant. So nothing changes. It's just a set of matrix multiplication without any update. And then another step that you can do is you quantize. So instead of using float 64, you can reduce them to float 16 or maybe just 8-bit for space. Let's say you want to put it in a small device, like a phone. No? And then you put this model on a TensorFlow serving node. And TensorFlow serving has some logic that you can update the model, and he will pick it up from the disk and start serving it automatically without having to shut it down. So it's good for production without having to remove the service. Now you have your cluster of serving. You put the new model will be picked up and be ready to be processed. Any other questions? Total clear. Huh?
Total unclear.
Ready for production. Ship it.
Are you going to post all of the iPython notebook on?
You should be able to reproduce easily. Yes, but the cluster will be down, so don't try it. Like you have to launch your own cluster.
Yeah.
And to launch the cluster, well, Google offers a cluster. You can go on the Google Cloud Computing, and you launch the cluster, and you will specify. If you want to see another example, there are some examples inside the TensorFlow, and it's inside TensorFlow-tools-distribute testing. Okay, and you can read here how to run the distribute testing. And there is a lot of code, and I had to go through and read it and figure out. There is also on GitHub. There is another project by Google that is the models, where Google just giving us all the models that they been working on. That's very good. And inside here there are someone that is inception distribute training. So inception is for image classification. You have a bunch of images and you want to recognize is a cat, is a dog. Now it's basically, this is almost state of the art. And there is one that is distributed train. And it has the exact concept that we show it today. So it has the TensorFlow the supervisor, okay? It has a bunch of other parameters to configure this. This is how Google actually launches it inside there. is production training system. Okay, so it will just go through and read all the variables that's inside there. Yeah, it's a lot of code. Good?
Okay, very good.
Thank you, guys.